In this video, we're going to define a group and we're going to prove some of the basic properties of the group. Alright, okay, let's start. Uh, let G be a non-empty set. Okay, to define a group, we need two things: a non-empty set G, okay, and a binary operation star on G. So, a function star which maps elements of G cross G to G itself. This, as we have discussed in the previous video, will be then called a binary operation on G. Okay, uh, so to define a group, we basically need an algebraic structure G star. Alright, algebraic structure G star. Now let's define a group. Okay, let G star be an algebraic structure. Okay, this algebraic structure is said to form a group. If the following conditions are satisfied. If the following conditions are satisfied. Okay, the first condition is that for all x and y belonging to G, x star y is in G. This is called closure property, and this can be omitted because by definition star xy, which is equal to x star y, should belong to G. Alright, they should belong to G, and this is any element in G star G. So x and y are any elements in G. So this is a consequence of the definition. So this particular property, this closure property, can be omitted from the definition of the group. Alright, the second condition is for all x, y, z belonging to G, we have x star y star z equal to x star y star z. Alright, this is called the associative property, as we have already discussed in the previous video. Okay, this is called the associative property. Now the third and fourth property are quite crucial, and the third property should be followed by the fourth property. Fourth property is the last property. Alright, the third property is that there exists some element G such that for all x belonging to G, x star E as well as E star x will be equal to x. Okay, this is called the existence of identity. This property is called existence of identity. And this E is said to be identity element element of G, the entire group G. Alright, now why is it so? It is so because this E is independent, since we have a statement of the form X for all Y Pxy of this form. Okay, since we have a statement of this form, X is independent of Y. Alright, so X, the value of E right here, does not depend on the value of X over here. Any value of X, okay, any value of X means for any X belonging to G. So for the entire set, by which we mean um, for any element X, the identity will be same. Alright, for any identity X, the identity will be E. It won't change for as per the value of X. That's what it means. X is independent of Y. So this E will be the identity for any given element of G, so, and won't vary. The value of E won't vary as per the value of G, as per the value of X, so we call it the identity element of G. This E will work for every X belonging to G, means it will work. It is a constant for every it's a constant for the entire set G. Alright, let's interpret it that way. Okay, that's why we call it the identity element of G. The fourth and final condition is that for all X belonging to G, there exists X dash belonging to G such that X star X, let's call it something like this, not dash, equal to satisfying this property, where E is the identity. Alright, this is called existence of inverse. And this element, since we have the statement of this form, we're going to say that we can conclude that Y depends on X. Y depends on X. So as per the value of X, the value of X inverse will change, and this X inverse is said to be inverse of the element X because the value of X inverse changes with X. So it will work only for a given value of X at a time. Alright, if we change X, the value of X inverse will change, inverse of X. Okay, that's all about it. And these conditions which the algebraic structure should satisfy, these conditions are also called group axioms or group conditions or whatever. Alright, these are also called group axioms. Now we can omit this because of the definition. We can include this anywhere. We can include this right here or somewhere in the middle or at the end. But whatever we do, we must state the existence of identity prior to the statement of existence of inverse, because this existence of inverse, the statement involving the existence of inverse condition, involves E. E means identity. So if we define the existence of inverse later on, we must have to define E separately. So let's not do that and simply define the existence of identity first and the existence of inverse later on. Alright, this should be the order: identity first, identity, then inverse. Alright, because the definition of inverse involves the definition of identity. That's why the condition for existence of inverse should follow the condition for existence of identity. Alright, okay, these are all about, these are the definition, this is the definition of a group. We're done with this. Now I'll discuss some examples in a separate video, examples of a group in a separate video. In this video we shall simply prove some properties, very basic properties related to groups. Okay, let's call them theorems. This theorem is called the uniqueness of identity. Uniqueness of identity. And it states that the identity element of a group is unique. We call it an identity element of a group because the value of the identity element does not depend on any value of the does not depend on the value of the does not depend on the element of the group that we're considering. Alright, let's prove it using contradiction. For the purpose of contradiction, if possible, assume that E1 and E2 are identities of the group G star such that E1 is not equal to E2. Okay, E1 is not equal to E2. So we're basically assuming that the identity is not unique, because had it been unique, E1 and E2 should have been the same element. Alright, now let's see, by definition of an identity, we must get E1 star E2, E2 star E1 to be equal to E1, because E2 right here is an identity element. Okay, so this is an element of G star, so X star identity star X should give X, where X is equal to E1. And similarly, E1 star E2 equals to E2 star E1 is equal to E2 as well, because E1 is an identity. E1 is an identity. E1 is an identity, and identity star an element is equal to element star identity equal to the same element as per the definition of an identity element. Alright, now these two imply that E1 and E2 are equal, because we already have star E1 E2 is equal to star E2 E1, and since this is a function, we cannot say that these two things, if this is equal to E1 and if this is equal to E2, we cannot say that these two are separate values, because a function assigns a unique value to an element of the domain. Alright, so these two cannot be different, and therefore we must have E1 is equal to E2. Let's compare these two statements. These two statements give us a contradiction. So our assumption that identity is not unique is false. So by the method of contradiction, we can conclude that the identity of an element of a group is unique. All right. The second condition, or the second property, is the uniqueness. Did I write uniqueness? Yeah. Uniqueness of inverse. Okay, uniqueness of inverse, which states that the inverse of any element x of a group is unique. So to prove this, we're going to use the method of contradiction once again. All right. To prove this, if possible, which means for the purpose of a contradiction, if possible, let x be an element, let the inverse of x belonging to G, where G star is a group, not be unique. So there are two inverses. So we can assume that we can consider inverses x inverse, x1 inverse and x2 inverse to be inverses of x, such that x1 inverse is not equal to x2 inverse. All right. Now let's see. x1 inverse can be written as x1 inverse star E, because x1 inverse, all the elements we've considered so far in the definition are elements of the constituent set G. Alright, this is it. So x1 star as it is, since x2 is an inverse, what can we write? X2 x star x2 inverse will give us E. Okay, because we are writing this because this follows due to the definition of identity, this follows because of the definition of inverse, and this follows because of associativity. We get this because of the definition of an inverse. We get this because of the definition of inverse. Okay, because since this is an inverse of x, we're going to get this to be equal to E. So x2 inverse, we're going to get x2 inverse, which is also because of A, not inverse. This is because of the definition of an identity, because identity star an element gives the same element. Okay, so what do we get? X1 inverse equal to x2 inverse. Thus these two statements they contradict each other. Contradiction. Okay, these two statements contradict each other, so we can conclude that the inverse of any element x of a group is unique. Okay, all right, now let's quickly look at some other properties. For example, A inverse, the inverse of A inverse is A itself. Now we can use the uniqueness of identity and inverse whenever we want from now on. All right, now let's see. A inverse can be written as something like this, Now inverse of A inverse can be written as, now for any given element A belongs to G, with G star being the group. Okay, being a group. Now we can replace E with A inverse star A. So now using associativity, we're going to get A inverse star A inverse star A. Now let's see. An element of the group is operated with, the binary operation is acting on an element and on its inverse, so this should be equal to E star A, and therefore we get A. This is how we prove that A inverse, the inverse of inverse, is the given element itself. Okay, very simple. Now this looks something like a result that we have been using for matrices if you have taken linear algebra. All right, if G star is a group, then x star y inverse is equal to y inverse star x inverse. All right, now let's see. What are we going to get? So let all right, we're already given this, we don't need to assume this to be anything. Let's see, x star y inverse star x inverse. Okay, now to be an inverse, if B is an inverse of A, that is B is equal to A inverse, then by definition we must have B star A is equal to A star B to be equal to the identity. Alright, so instead of A we have x star y, and instead of B we have y inverse star x inverse. So we need to show that this star this is equal to this star this is equal to E. Okay, this is equal to, now since we have associativity, now this is not so trivial to obtain, but Hungerford's algebra has given a discussion regarding why it's possible. We're going to use that. It's possible. We're going to use this result. We're not going to prove it right now. Okay, since we have associativity, we can put the parentheses wherever we want, like this, star x inverse. Now this means this is the identity element times x inverse. We can add or remove the parenthesis however we want, since we have associativity. One thing to remember is that if we have an associative operation, then parentheses or brackets, parentheses, can be added or removed as per our need. Okay, so now using the parenthesis over here, we're going to get x star x inverse, which is equal to E. Now on the other hand, y star y inverse star x inverse star, something like this, we can put the parenthesis somewhere over here. This will be E, so y inverse star E star y. Now let's put the parenthesis here. Something into identity means identity, so sorry, the other element itself, which gives E. So we see that A star B, B star A is equal to E. So from these we can conclude that x star y inverse is equal to y inverse star x inverse. Okay, that's how we do it. And let's look at the other properties. One of the most interesting properties that is the left cancellation law. Cancellation law. Alright, left cancellation law. This means if x, y, and z are elements of a group G star, then x star z is equal to y star z if and only if x is equal to y. Okay, x is equal to y. Now to prove this, let's see. Let's prove this part first. Okay, then we'll prove this part. All right. Left cancellation. Sorry, this is the right cancellation law, because this we are going to cancel out these two z's. All right. So this is right cancellation law. Right cancellation law. Now for this part, let's see. We're going to assume x to be equal to y. Then the order pair xz will be equal to yz. So since star is a function acting on G cross G, we're going to get xz to be equal to yz, because this, if the inputs are equal in a function, the output should be equal. So this basically means x star z is equal to y star z. Now if we have if we have x star, let x star z be equal to y star z, then operating both sides we can operate. Then let's see, x star z star x star z, let's see, x star z star z inverse will be equal to y star z star z inverse, because since x star z and y star z are equal, okay, these elements are also equal, so the binary operation will give us something like this. Now using associativity we can do something like this. And since this gives the identity element, we can say that x is equal to y. Alright, this proves the right cancellation law. The other one is left cancellation law. Left cancellation law. The left cancellation law states that if x, y, z are in G, with G star being a group, then z star x equal to z star y will hold if and only if x is equal to y. Or we can also state it like this: x star z, x star y equal to x star z if and only if y star equal to z. Anyway, you can give any kind of statement, but make sure that we are going to cancel the same quantity towards the left side. Okay. Alright, since x is equal to y, to prove this, let's consider this part first, then we're going to consider this part. To prove this part, x equal to y implies that these ordered pairs are equal. Since x and y are equal, the second components are equal, and z is equal to z, so the first components are equal. So we're gonna have that these two ordered pairs are equal. So taking them as inputs in the function star, we're gonna get the same value, which means z star x is equal to z star y. Alright, now for this part, let's take z star x to be equal to z star y. Then, as before, z star x and z star y, these two ordered pairs will be equal. Okay, these two ordered pairs will be equal, so star of these two elements will be equal. This will give us z inverse star z star x equal to z inverse star z star y. Using associativity, we can write something like this. Now since this gives the identity, we can say that x is equal to y. This proves the left cancellation law. Alright, left cancellation law. Finally, we're gonna prove this thing. Let AB belongs to G. Then first one is that there exists a unique X belonging to G such that X star A is equal to B. Okay, X star A is equal to B. And the second part is that there exists a unique X belonging to G such that A star X is equal to B. Okay, so existence and uniqueness proofs. So first of all, for this part we're going to show that there exists X belonging to G such that X star A is equal to B, and then prove that the value of X we have considered is a unique value. For this part we're going to show that first we're going to show the uniqueness, and for this part as well we're going to show this first and then we're going to show the uniqueness. Okay, this will be the last property we're going to discuss in this video. Okay, for the first one we're going to need a value of X. We are going to assign a value of X. Okay, assign a value of X. Now what will be that value? Let's see. We need B over here and we need this A inverse. We need this A to be removed. So let us define X to be equal to B star A inverse. Then let's see, X star A is equal to X star, B star A inverse star A, which is equal to B star A inverse star A, which is equal to B by definition of inverse. We got this because of associativity. Alright, so we have proven the existence of X. There exists, the existence part is complete. Existence part is complete. Okay, existence part is complete. Show the uniqueness. Let, if possible, let this X not be unique. Then we can get two values of X, that is X star A is equal to B and X2 star A is equal to B, such that X1 and X2 are not equal. Okay, we can obtain something like this. Okay, so from here what can we say? X1 star A is equal to X2 star A, and by the right cancellation law we can get X1 is equal to X2. Now let's see this part of the statement and this assumption. These give a contradiction, so this statement is wrong, and therefore the uniqueness of X is also established. Okay, now for the second part, let us define X by, let's see, what do we need? We need B over here, we need B, but we need A removed. Now if we take B star A inverse, we cannot directly remove uh, A from the left hand side. So let's try to remove this A first and then operate it with B. So if we take X equals A inverse star B, X to be A inverse star B, then A star X is equal to A star A inverse star B. Using associativity, we're going to get something like this, which will give us B because this is an identity. So the existence part is complete. We have defined an X by ourselves and we have shown that the defining the given condition or the given equation also holds. So this establishes the this establishes the existence part. Now for the uniqueness part, let's proceed as before. If possible, let this X not be unique. Alright, not be unique. Then we obtain two values of X. Let's say X1 and X2, giving us the same value B, such that X1 and X2 are not equal. X1 and X2 are not equal. Now from this part, since B is equal to B, we're going to get A star X1 is equal to A star X2. Alright, and from the left cancellation law, we can cancel out these two A's and then obtain X1 to be equal to X2. Now this part of the statement contradicts this part of the statement, so we've obtained a contradiction. So this assumption which we made is not correct, so the value of X should be unique. Okay, this establishes the existence as well as uniqueness of X. Okay, now we can restate this theorem as there exists unique solutions to the equations A star X equal to B and B star X, sorry, A star X star A equal to B, where A, B, X are elements of the group G star. Okay, something like this. This is an alternative statement of these two statements. Okay, and this is what we usually encounter in the textbooks. Alright, that's all for today, and in the next video we're going to discuss some examples of a group. Alright, that's all for today. Thank you very much.